All right, so now we're going to talk about manipulating KEQs mathematically, or what happens to KEQ when we manipulate the equation might be a better way of putting it. Which, oh, hey, I did there. All right, that works, cool. So first trick is, well, what if we, flip our reaction? We reverse the reaction. So all of our reactants become products, all of our products become reactants. What does that do to KEQ? And so if we go like A plus B gives us C, this is an equilibrium system, as you can see, clearly denoted by the arrow. We flip that, and now C becomes A plus B. Well, our forward reaction, our initial, is just C over A times B, concentrations. If we reverse it, guess what? We flip it. We flip our K, because now our products are A and B, they go on top, our reactant is C, it goes on the bottom. And so if we reverse a reaction, we just go 1 over the forward. So if we know that, like, our initial K value was, 7. Well, the reverse reaction is going to have K is 1/7. 1 divided by 7. So it becomes an inverse relationship. The next one, what if we start manipulating our stoichiometric coefficients? Not unbalancing it, but maybe we divide the whole thing by 2, which is what I do here. Or maybe we multiply the whole thing by 2. Well, we'll talk about the general in a second, but if we have something like AA plus B moles of B gives us C moles of C, so we get a little more specific now. Now we got stoichiometric coefficients that aren't necessarily 1 like they were before. And we do, multiply by 1/2, we divide everything by 2, so now we have A over 2 moles of A plus B over 2 moles of B gives us C over 2 moles of C. Yes, this is exciting to hear live as it is recorded, I know. Again, we just divide everything by 2. Okay, this is still a balanced chemical equation. It's just balanced differently. Well, if our initial looks like this, our standard form, C to the power of C, that's our product, divided by our reactants to the power of their stoichiometric coefficients. Well, now all of our stoichiometric coefficients are divided by 2. That means all of our powers have been halved. And so what it is we take our initial K value and we put it to the power of whatever we multiplied by. So in this case, it's the power of 1/2. But if I had multiplied everything by 2, it would be to the power of 2. If I had multiplied across by 10, it would be K to the power of 10. So it affects the K value exponentially. So that's why we always have to have some standard form that we write chemical equations in. I mean, 1, we want, minimum balance level possible. But 2, we were actually kind of priming you secretly for this chapter. So now you know how to write the best version of a chemical formula. And so generally you're not doing something like this because the number for K is going to change. If your K was, 2 before, now it's going to be 2 to the 1/2 or square root of 2. Those aren't the same number. So you got to watch out. So it turns out how we write chemical equations is really important for equilibrium constants because it feeds into the standard, we have to have a standard approach. We have to kind of like standardize everything. And so that's what we were teaching you to do in the early chapters. All right, and so now I promised you something like Hess's law. And of course you can't spell Hess's without 3 S's. Yeah, that one never gets old, right? So what you do is if you can combine multiple reactions like 2 or 3 or 4 or 5, however many, you just multiply all the K's. That's it, for however they're combined. So you might have to do some tricks like this, you might do some tricks like this, like you did in Hess's law. But once it's set up, we have our equations, they sum to the equation that we want. We just use these K values for these equations as they're written, we multiply them together, and we get the final one. Now I'm going to do this one a little bit differently than the other two. It's a little more involved. So I'll do a specific example like I've done because you want to show some reactions. I don't want to be like A, B, C, D, E, F, G. I don't want to just work the alphabet. That's kind of boring. So these are actual reactions. We can sum to get another one. And so if K final is equal to K1 times K2, let's prove it, right? Let's prove it. Let's put our money where our mouth is. Let's prove this. So here's my expression for K1. Product squared divided by reactant divided by reactant. Boom, boom, boom. Times my expression for K2, so my equilibrium expression right here. Product squared divided by reactant, reactant. Oh, and one of those reactants is also squared. If I multiply these out, my NO squared here cancels my NO squared there. So no more, no squares, right? Those are gone. And so now I have this guy divided by this times this times this. Well, that combines to be O2 squared. And guess what this is? Guess what this is the equilibrium expression for? This reaction right here. 2NO2 gives us NO2 squared. 2O2, O2 squared, into n to the power 1. So it proves that it works. Now, generally, are you going to be doing it this way? No, generally you just be like, oh, this one's 5, that one's 7. That means my K final is now 35, or whatever it is. Or this one's 5 and this one's 1/5. Now my K final is 1. You just plug them in and solve. You know, same deal here. But keep in mind that these two can feed into this one if you got to do kind of like a Hess's law sort of thing with equilibrium constants. Just be aware. All right, so these are kind of the mathematical tricks to manipulate K's and get what you want out of them, right? Nothing like a little manipulation. Okay, so yeah, nothing too exciting here. It's basically just math. You know, it's not. There's no real chemical stuff to figure out. The main thing is like, well, there's a reason we really try to standardize how we write chemical equations. Turns out it's really important for equilibrium constants. So if you look up a number in a book and you see like 37, you don't want to write it wrong because then your K should be like 37 square rooted or something. So you got to watch out. Okay. So anytime you got to manipulate an equation, this is what it'll do to K. And I know SmartWorks got a few problems on it, so I always want to talk about it. And, you know, I never pass up an opportunity, apparently, to drag Hess's law in any chapter I can as well.